that you just did on determining the enthalpy change of combustion of a fuel, we looked at the enthalpy of combustion of ethanol, methanol and propanol. I'll start by defining the enthalpy change of combustion. I'd like you to learn this definition. We talked about it a bit earlier on, but it's one of those definitions that we're going to have to learn for this course. This is the kind of thing that will go on flashcards. So this is the enthalpy change when and lots of the definitions in this topic start the enthalpy change when 1 mole of a fuel or a compound, doesn't have to be a fuel, in this case it's a fuel, let's say a compound or a substance even, let's say substance is completely burnt in excess oxygen, right? So the excess oxygen bit is clearly evidence we want to talk about the fact that this is a complete combustion process going on. We also need to add to this definition that all of the reactants, sorry about my writing, all of the reactants and products are in their standard states. I'll tell you what that means in a minute. And under standard conditions. It's a meaty old definition that you're going to have to learn, but you'll start to realise all the definitions we need to learn for energetics topics, standard level and high level, with lots of similarities. But that symbol there refers to standard conditions. And that means 298 Kelvin. In fact, in your data book, I think it says 298.15 Kelvin, 100 kilopascals. If there's a gas present, and it's not relevant to this one, but standard conditions will have concentrations at 1 mole per litre. But here we need to worry about the temperature and the pressure of everything. And the standard states are the states of the substances in the balanced equation when they're in standard conditions. So for example, the ethanol and methanol were liquids. Oxygen, of course, is a gas. Carbon dioxide is a gas as well, but we were producing water as a vapour in this reaction, but we have to consider that in its standard states it have to convert back to a liquid again, and there's an energy change associated with that. So an example of an enthalpy change of combustion will be, as we wrote down earlier on, the complete combustion of liquid methanol in the presence of gaseous oxygen to give carbon dioxide and water in its liquid state, like so. And so what you get is whatever the reactants or the elements in the reactant are, they will be fully oxidized. So carbon, when it's fully oxidized, will become carbon dioxide, and the hydrogen, when it gets oxidized, is turning into water. Right, so that will do for that for now. We'll spend a fair bit of time thinking about enthalpy change of combustion in due course. But today is about how do we measure that using calorimetry. And so just remind you that you had a calorimeter, that copper tin, essentially copper tin, that makes no sense, so that copper calorimeter that you had, and that contained water which we were heating up. We started with water at, I think you probably were saying, about 20 degrees. I'll refer to that again in a second. And it was of a known mass, which was 100 grams, which you worked out because we know that 1 gram, the density of water is 1, so 1 gram is equal to 100 centimetres cubed. So you measured using a measuring cylinder 100 centimetres cubed of water. And we took that water, we measured the temperature with a thermometer, made sure it had equilibrated and reached room temperature, and then we had underneath a spirit burner, which looks something like that with a wick. Excuse my drawing. But you've got a spirit burner burning away there and heating up that water, and the temperatures of the water would increase. So just reminding you what we did. So the temperature of the water increased while we were stirring from, say, whatever it was, 20 up to about 70 degrees. And so there was a delta T, 50 degrees C. The mass of the water was 100 grams. And we're going to use that to work out the energy transferred to the water when we burnt that fuel. And so we also need the specific heat capacity of water, which is 4.18 joules per gram per degree C or per Kelvin. I think it's degree C since we're measuring in degree C here. So joules per gram per degree C, okay? Or if you prefer, joules per degree C per gram, whatever works for you. Now at physics GCSE you were probably given that in kilojoules, and you were probably told it was called delta theta. But in chemistry textbooks, for whatever reason, it's given as delta T, and we use it in grams. Now, what you'll have learnt in physics that Q, which is the energy transferred in joules, it's really important that you start to learn and make notes that this is joules. And I will reiterate it, of course, and I'll keep reminding you when we're practicing. But it's important you realise this is in joules. And it makes sense, doesn't it, from the information you've got up here. It's joules per gram per degree C. Please make a note of that. And that is equal to the mass of the water, not the mass of the methanol, but the mass of the water. Working out how much energy has been transferred to water in grams, times the specific heat capacity, times delta T, and we're quite happy to leave this in degree C. If you convert to Kelvin, sometimes I do enjoy this little mistake that people sometimes make. It's completely understandable but wrong. So some people attempted to convert the change in temperature into Kelvin by adding 273. But that's daft, isn't it? Because if you've gone from 20 to 70, it's gone up by 50. If you did that in Kelvin, it would be 293 to 343, which is also a change of 50. So the delta T is the same in Kelvin and degree C. All right, so don't add 273 to the change in temperature, please. Right, so that's how we work out how much energy has been transferred to the water. What we need to do in this topic, though, is work out how much energy was released per mole of fuel burn. So we can do that by saying the enthalpy change of combustion using this piece of equipment. I'm going to put a standard there, even though the conditions might not have been exactly standard conditions, because it might not have been 298 Kelvin in here. We might not have had the water going back to liquid water and all of these things, but I'll leave it like that, is equal to Q, which is the energy transferred to the water, divided by the number of moles of the fuel. Now, this reaction is exothermic. There's more than one way to do this, but the way that I like to do it is if it's an exothermic reaction, we just put a minus in front of it, and if it's an endothermic reaction, we'll put a plus in front of it. You can go about it a different way, and I think it's overcomplicated. But we work out the moles of fuel by doing N is equal to the mass of the fuel divided by the MR of the fuel. And that was the mass change that you found when you before and after you burnt the fuel. So you had the lid on, you burnt the fuel. No, you had the lid on, you measured the mass of the fuel. You took the lid off, you set fire to it, you heated up the water, you put the lid on, you measured the mass again. So that mass there is the change of mass of the fuel, or of the spirit burner really. If you want to label this spirit burner, it might be good as well. Spirit burner, that's this thing. And you got the wick is this thing here. Alright. So that's what you've got to do. And I think what we'll do now is actually look at our data, and then I wonder actually. I think what we'll do, we won't look at our data now. We won't plug our numbers in. We'll do that next lesson. But I gave you a challenge during the practical to think of as many potential sources of error as you possibly can here. We're just going to brainstorm them. We won't go into loads of detail. We'll think about some sources of error, and what I'll do is I'll pause the video, you can chuck them at me and I'll discuss them on the recording afterwards. So some example sources of error, I'm sure there are more, but we're running out of time. So there's obviously the heat loss to surroundings is the big one, particularly from the flame. We could see the flame wafting around, you could feel the heat coming from the flame, and the heat is licking around the outside of the calorimeter, not transferring heat to the calorimeter. So obviously the biggest one by miles, so well done for getting that first. The water's heating up to 70, 80 degrees in your experiments, which means the water is also going to cool down, because we didn't insulate the calorimeter at all, nor did we have a lid, and so heat will be lost from the water too, reducing the measured temperature change, reducing delta T, reducing the value for Q, and reducing the value for delta HC. Some of you suggested that it could be mass loss from evaporating fuel. Now, in that time when you've taken the lid off and set light to it, you might have lost a tiny bit of fuel potentially. That will change your results, and you can work out how. There might be some incomplete combustion, almost certain, well there are certainly some incomplete combustion going on. Evidence for that would be the soot on the bottom of the calorimeter. The yellow flame, that's a massive deal, that's going to lose you. So that one and that one are huge issues and make a massive difference. There might also be some evaporation of water that would change the mass of the water. Or also, if you sweat, you cool down, the water's evaporating will actually cool down a tiny bit. So that has a double effect. It has an effect of increasing and decreasing, or making the reaction appear to be more and less exothermic at the same time. Which of those factors is bigger? Hard to work out. Was there any unburnt fuel that was evaporating beyond just evaporating here? Probably some stuff that didn't get burnt completely at all. There's lots of possible sources of error here, which we need to be thinking about. And these are the kind of things we think about when doing coursework next year, and writing about them, and the effect that each of them would have on our measured and therefore measured value for delta HC. That will do. We'll wrap up with a reminder of what's coming next.